In this figure, we're looking at the multiplicative one-period binomial framework. Notice that there are two arcs. There's a positive arc and a negative arc. The underlying stock price is assumed to grow at some total return U times the stock price. So if the stock grows by 10%, U would be 1.1. And then if the stock declines by 10%, D would be 0.9. And so the key is that the option call or put is a function of the value of the stock if up occurs, if the positive arc happens, and then if the negative arc happens, the option value will be denoted O sub D. And so there's assumed to be a single period. We're assuming a binomial process. There are only two arcs. We're going to create a hedge portfolio, and from that we're going to derive an option value and provide a numerical example. And so in the case of a call option, if up occurs, then I know at the expiration of the option, the value of the call option is the maximum of 0 or the terminal value of the stock minus the strike. And the same is true if the down arc occurs. And the stock will either go up to single value or down to a single value. It's important to note that this is an unrealistic assumption, and we'll relax that assumption as we go to a multi-period model. Consider if we go long H shares of stock, that H is eventually going to denote the hedge ratio. But if we go long a certain number of shares of stock and we go short one call, if we solve for the H that yields the identical future cash flow, we can compute the hedge ratio. And so in this particular process, the value of this portfolio, if up occurs, is number of shares that I own in the stock minus the liability that I have from shorting the option. And you get the same sort of pattern with the down arc. And so I can solve for the optimal hedge ratio, which is going to work out to be just the change in the call, the value of the call if up occurs minus the value of the call if down occurs, divided by the change in the stock. So the hedge ratio is simply going to be the change in the call divided by the change in the stock, where this change is taken at the terminal point in time. The way we're going to value this is the value of the option today should equal to the hedge ratio minus some financing amount. And I'd encourage you to look in the text materials provided with this chapter to understand that the no arbitrage approach to call valuation gives the identical mathematical result as the present value of the expected terminal cash flow of the call, where that expectation, the probability, is based on the equivalent martingale measure probability, which is simply the total return of the risk-free rate minus D divided by U minus D. This financing amount is basically just how much money do I borrow in order to create a synthetic position in the call. And so one thing we see immediately from the single period model is that a call option can be thought of as buying stock with a certain amount of margin. And so call option is simply a leverage position in the stock where the degree of leverage changes over time, as we'll see. So if we work out a numerical example, suppose the stock price is 99, the strike price is 100, the risk-free rate is 2%, time to maturity is 1 year, and U is 1.25 and D is 0.8. You can verify these numbers at your leisure, but based on these inputs, I can compute a variety of different outputs, including the payoffs if up occurs or the payoff if down occurs, and the hedge ratio in this case is 0.5331. Based on these numbers, we can compute the theoretical value of the call as $11.38. And if we use the equivalent martingale measure approach, we get exactly the same number. And so we have now our two theoretical models, the no arbitrage model, which is basically buying stock with borrowed money. And so in this case, I'm going to buy $52.77 worth of stock. I'm going to borrow $41.39. And so a call option can be thought of as a leverage position in the stock. An alternative way to come up with the same valuation is simply taking the present value at the risk-free rate of the expected terminal payout, where this expectation is an objective probability known as equivalent martingale measure solution. It's also known as the risk-neutral probability. So a single period put, it's derived in a very similar fashion. In this case, the put option, if up occurs, is x minus u times S0. Remember, if the price goes up, then the value of the put goes down. Thus, we see a clear similarity with call options. This is a binomial model with two arcs, a single node initially and two nodes at expiration. We're going to follow the same strategy as with the call option. We're going to buy H shares of stock and buy one put, solving for H yielding identical future cash flows. That is, we want the terminal value, if up occurs, and the terminal value if down occurs, to equal each other. If we set these two values equal, then this particular portfolio will be riskless, and therefore we can discount it at the risk-free rate. And so the result of this is we get the optimal hedge ratio, which is simply the cross-sectional change in the put at expiration divided by the cross-sectional change in the stock, again at expiration. And what we observe is the value of a put is simply some lending less a position in the stock. It's going to turn out that this no arbitrage value for the put is equivalent to the present value of the expected terminal payout, where the expectation is taken under the equivalent martingale measure. This would be the financing amount, and the equivalent martingale measure probability would be the same. This is also often called the risk-neutral probability measure. Again, if we look at a set of data, the several intermediate calculations, I'd encourage you to look at them carefully. At times, this hedge ratio might be represented as the price of the up minus the price of the down, putting a minus sign here. It's really arbitrary, but the hedge ratio in this case is 0.4669. With this result, I can compute the value of the put as $10.42 using the no arbitrage model. If I use the equivalent martingale solution or the expectations approach, I get exactly the same number. The two models yield the exact same value. In a two-period model, we're now able to explore a variety of different aspects. Again, remember that the geometric Brownian motion version is multiplicative. It recombines the terminal value. If up occurs twice, I get this call payout and this put payout. And if the stock goes up then down or down then up, because it's recombining, this will be the payout on the call. This will be the payout on the put. And if down occurs twice, these are the corresponding payouts. And so a two-period binomial lattice, if you'll notice, going up then down yields the same result as going down then up. And so this is basically a two-period tree. If I carry along some data, I can calculate the value of the call today as $12.56. And one of the key observations is if both nodes emanating from a prior node are zero, then the value of the option obviously is zero. And when there is a positive value, then there'll be some value here. And then we can, based on backward recursion, get back to this value. If you notice that the hedge ratio actually goes up when the stock goes up, and remember that the implication is that I'm buying more shares. And so basically the implied trading strategy is buy when the market goes up and sell when the market goes down. The goal here is not profit maximization, rather the goal is to replicate the payouts on the call. And so the two-period European-style binomial put follows the same procedure. In this particular case, two out of three nodes have a positive value. Therefore, I have positive hedge ratios at time step 1, and the put value in this case is $9.68. If you're new to this area, I would recommend that you work through some of this math just to improve your familiarity. American style options can be exercised early, and that potential needs to be incorporated. The way this is going to work is what's known as the method of backward induction. I'm going to start at the terminal value and reason backwards through time. The goal is to establish the sequence of optimal actions. American style and dividends, there's a couple different ways to handle dividends. One is assume a constant rate based on the stock price. The other is to place the present value of dividends in escrow. The idea of escrow is that it is bankruptcy proof. And then based on the escrow method, what I'm going to model is the stock price less the present value of dividends over the life of the option. And then assess early exercise decision at each node. So a 2-period American style binomial put. The key thing to notice is that the value of the put, if down occurs, it is $20.80 in the money. Remember, the strike price is 100, and the stock price is $79.20, and therefore it's $20.80 in the money. But the European style put value is only $18.84. The requirement that I have to wait for another period in order to receive a payout, and that payout is uncertain, leads to the European style put only having a value of $18.84. Because this is American style, I will choose to exercise early as the buyer of the put. That choice will yield me $20.80, and therefore the value today, knowing that I will make that choice at time 1, if down occurs, increases the value of the put. So an American style put option, in this example, the American feature has a positive value. In order to build multi-period models, we need what are known as coherence conditions. We don't want to build out a theoretical model and have it have intrinsic arbitrage opportunities within the theoretical model. And we can avoid that if we assume a no arbitrage boundary condition. That is, the total return on the risk-free rate has to lie between the total return if down occurs and the total return if up occurs. The probability condition is simply that the equivalent martingale measure probability can't be, quote, too close to 0 or too close to 1. We'll illustrate what the implications are there. Just as a general rule of thumb, just set that to be a half and your problems go away there. The no arbitrage condition is that the equivalent martingale measure probability of an up has to equal to the total return if I invest in the risk-free rate minus the total return if down occurs divided by the difference between up and down. The variance condition, the goal here is just to make sure that the assumed standard deviation, the local standard deviation, is constant throughout the tree. In order to have this variance condition, this equality has to hold. The reason why you want to just choose a half is illustrated here. You can read in the text to get more technical details. But if you let the probability get too close to 0 or too close to 1, the up and down moves become unstable. Clearly, e to the minus 131 or e to the minus 125 is just begging for machine error kinds of problems. And so if you just stick in the neighborhood of half, that basically resolves that problem. We can model, if we're going to write up option valuation with R code, it's helpful to be able to model both calls and puts within the same function. If I use an indicator function where +1 means it's a call, -1 means it's a put, the terminal payouts look something like this.